Hey everybody, thanks for joining in. This is the John Boat Dolly system created by myself, Jacob Fowler. In this presentation, we'll be going over the defining moments, research, design, building, testing, and the conclusions of this project. The define phase, first we defined our objectives. We found that the dolly needs to be able to transport over tough terrain. I also found that the dolly needs to be rigid enough to travel over that terrain, and it also ergonomically designed for the operator. The main problem is the amount of force required for an outdoorsman to transport a John boat and his or her equipment from one lake to the next. The goal of this project is to reduce the force required to transport a John boat and its equipment from 176.8 pounds force to 88.4 pounds force, which is 50% by April 30th, 2020. Deliverables. In order to deem this project a success, the dolly design must meet the following deliverables. The dolly must weigh less than 70 pounds because the operator must be able to maneuver the dolly system around. We figure if it was heavier than that, they wouldn't be able to efficiently and effectively move the dolly system around. It must be rust resistant since it will frequently be around water. Dolly must be able to carry a capacity of 500 pounds. And reduce the amount of friction and force required to move the boat by 50% as previously stated in our project goal. Our Gantt chart, we define this through the several different phases. We have the research phase, design, build, working on the final report, and our final test. Research, the big debate was steel versus aluminum. While each have their own pros and cons, steel was the final choice, mainly because of the strength and cost of steel. The deflection and critical buckling point was calculated for aluminum and steel. As you can see on the right, steel was much stronger than aluminum. Steel was 11.377 inches worth of deflection, and aluminum is 32.99 inches worth of deflection should 500 pounds be shifted to one side of the dolly. Although the 11.377 inches of deflection for steel is good, we wanted to reduce that even more. So in order to do that, I introduced a concept where if we bent the wheel mounts to 90-degree angles, we could reduce the deflection even further. This is a draft of the original design and the final design on the right. On the left, you can see that there were no 90-degree angles, and the deflection, should the weight be shifted, would be way too high for this design. So on the right, we made adjustments. As you can tell on the wheel mounts, we also added steel C-channel to the base of the top plate to reduce any flexing in the material during transport. The steel C-channel adds to the rigidity. Here's the final rendering of the design. As you can tell here, the wheel mounts are 90-degree angles, and the C-channel has been placed under the top plate. Purchasing and cost. All materials were purchased at Tractor Supply or Southern Steel. The total cost for the project, including delivery cost, was $266.73. There is a minimum purchasing size at Southern Steel. We had to purchase a 4-foot by 8-foot 12-gauge steel sheet, and we also had to purchase a 20-foot steel rod. The first process to the building process or building phase is to find a plasma cutter, at which point you will plasma cut the top piece and all of the wheel mounts, including the axle holes. Once that has been completed, the best thing to do is to go find a box brake and use a box brake to bend the 90-degree angles into the wheel mounts and the 45-degree angles into the top plate. Once that's been completed, use a horizontal bandsaw to cut the axles to the appropriate lengths, which is 34 inches. Since this is the 20-foot rod, we actually have 7 34-inch axles should the original be bent or needs to be replaced. After that, it's the welding process. We outsource this to a teaching instructor at More Technologies by the name of Stephen Haltman. He MIG welded the wheel mounts to the base of the top plate. The reason that we outsourced it was because the amount of weight that this dolly system would be under and would need very strong welds, and I don't have enough trust in my own welding expertise for that. Once he was finished with that, I was able to use a Lincoln 110 MIG welder to tack weld the C channel to the base or bottom of the top plate. Drilling: a vise, tap, drill press, and drill bit are needed for this process. The reason that a tap is used is to create an indentation in the steel to keep the drill bit from walking during the drilling process. The vise holds the axle in place during the drilling process, and a 5/16 inch drill bit is used. Once the drilling process is finished, I would suggest using sandpaper or some sort of bench grinder in order to sand down the edges of their hole to make the safety pins be able to slide in and out easier. This is the John Boat dolly system completed. As you can tell here, it's been painted with a Rust-Oleum product to keep it from rusting. The top plate has 45-degree angles to keep the John Boat from sliding left to right during transport. The C channel has been welded to the base of the top plate to add with rigidity. Each wheel mount has been MIG welded to the bottom of the top plate, and they've also been bent to 90-degree angles to decrease the deflection. The axle is removable. As you can tell, the safety pins hold it in place, but once those are removed, the axle can be removed should the axle need to be replaced, or if one of the tires needs to be replaced, you have the ability to do so. This is a testing demonstration of the John Boat dolly system and the John Boat. The first video is how to effectively and efficiently mount the dolly system to the John Boat. First thing to do is to pick up the stern of the John Boat and place it on the edge of the dolly system. Once that's in place, you simply pull the boat back and push the dolly forward using the axle, and it slides into the proper place. Once the operator's finished doing that, they can go pick up the bow of the boat and move the boat to where they please. The next video is operating the John Boat, so it's a combination of transporting the dolly boat around as well as unloading the dolly from the boat. Once the operator has finished moving the boat around, they simply set it down, walk to the stern of the boat. Once the boat is picked up off of the dolly, it slides out of place, and at that point the operator can rotate the John Boat off of the dolly. Final conclusions: the project met all deliverables defined. The total weight was 68.2 pounds. The original deliverable was 70 pounds, so we are under that weight. The dolly system was painted to resist rust. That was a deliverable that we needed to meet since it will frequently be around water. It can carry more than 500 pounds. It's rated to carry 660 pounds due to the limitations of the wheels, not the design or the steel. Reduced force to require the transport the boat by 97%. So I originally found that 176.8 pounds was what it would take to move the boat on a flat surface without the dolly, and it was able to be reduced to 4.6 pounds to move the boat on the dolly. Acknowledgements: I'd like to thank Stephen Haltman with More Technology for all the welding help, Dan Perkins at Hidden Safes for letting me use his drill press, Professor Hewitt at the University of Memphis for helping me understand deflection and how adding a secondary axis would decrease the deflection, Matt Hale at the University of Memphis for helping me with the plasma cutter, and Barry Wymore at the University of Memphis for helping me with the horizontal bandsaw. And that concludes this presentation. Thank you for tuning in.